Hello everybody. Today what we're going to do is we're going to observe that there are certain elements in the periodic table that don't follow the normal electron configuration pattern. They're known as anomalies, and there's several elements that do this. We're going to focus on the 5 most common ones, okay? And these 5 elements, 2 of them are found right over here. It's chromium and molybdenum. And these 2 elements are in what we call the D4 column. As you recall, this is the D block of the periodic table. The other 3 exceptions are over here, and this is the D9 column. And these elements are copper, silver, and gold. Now, what I'm going to show you is why there's a reason why they don't follow the normal pattern. So let's take a look closely at chromium and copper. We're going to look at those 2 first. So if you look at chromium, chromium is number 24, and it's in the D4 column. If you do a normal electron configuration for chromium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it's 3d4, okay? Now, here's what I'm going to do. I'm going to go ahead and do the noble gas configuration for this. If you recall, the first, to do the shortcut here, argon represents the first 18 electrons. So what I'm going to do here is I'm going to put argon, and then I'm going to put 4s2, 3d4. Now, I'm going to demonstrate why chromium is an exception. This is the expected configuration. However, in real life, chromium does not show this. Okay, if you do an orbital diagram and you put 2 here in the 4s, and then when you do the D, you got to draw a total of 5 boxes, and you follow Hund's rule, and you put 1 in each. Notice, here's what's going to happen. There's an empty room over here. And what happens is this electron over here sees that there's an empty room, and it rather jump right over here and occupy this empty room. And in doing so, it does no longer need to be paired up with the other electron from the 4s orbital. So the reasoning for this is it is more stable for that second electron to fill in this empty room that is not being used, and that way all the electrons have their own individual room or orbital. So what happens is the electron from the 4s2 jumps over. So the actual electron configuration for chromium would not be 4s2, it would be 4s1, and then that other one that jumped over fills in that d orbital, and it becomes 3d5. Now, the same thing that I just did happens with molybdenum. If you notice, molybdenum is right underneath. Molybdenum is number 42, and the shortcut for molybdenum is krypton, okay? And then it's 5s2, 4d4. But what's going to happen is the exact same thing I just explained with chromium. This one's going to jump over here, and what's going to happen is molybdenum is going to have an actual configuration of 5s1, 4d5. Okay, so you could see that these 2 elements are exceptions to their normal pattern. Now, the other elements that also do this are copper, silver, and gold. Copper is in the, it's number 29, okay? And the electron configuration for copper would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it's 3d9. Those are your 29 electrons. The shortcut, or the noble gas configuration for copper, would be use argon for the first 18 electrons, and then you're going to put 4s2 3d9. Now the same thing's going to happen. I'm going to illustrate that there is 2 here, and then when you use Hund's rule, and remember there are 5 boxes for the d orbital, and you fill them in, you go 1, 2, 3, 4, 5, then 6, 7, 8, 9. Now you might be wondering, what's the difference between having, 2 over here versus 2 on this side? Well, what's going to happen is it actually rather jump over here. If you look at it, by jumping over here, the 3D level is completely full. It's actually more stable to fill out the 3D before you fill out the 4S. So what it prefers is, instead of pairing up over here originally with the 4S, it would rather jump over here and completely fill the d orbital, and in doing so it actually becomes more stable. So the electron jumps from the 4s2 to the 3d9, and the actual configuration for argon ends up being 4s1 3d10. Now if you look carefully at the periodic table, underneath you have silver and gold, and silver and gold are going to do the exact same thing. Okay, silver is number 47. So if you do a shortcut for silver, we're going to use krypton as the noble gas, and then silver would be 5s2 3d9. And the same thing is going to happen that happened with copper. The electron from the s is going to come over here and fill in the d orbital. And what you see here on the left is the actual, what you expect the silver electron configuration to be. But in reality, silver will be like this. It will be 5s1 3d10. So this is the real configuration. Again, it's an exception to what you would normally expect. And just to show you this, gold, which is underneath silver, all 3 of these elements are in the D9 column of the periodic table. They're all transition elements. Gold is number 79. And if we do a shortcut for gold, it would be xenon, and it would be 6s2. Oh, and I just noticed something. Let me fix this here. I apologize here. This was a 4d9. I just realized that. So silver is 4s2, and I got to fix it over here as well. Didn't catch that when I did this originally, but now it's fixed. Okay, and let's go back to gold here for a second. If you look at gold, it's going to be 6s2, and then it's going to be here 5d9. And the same exact thing is going to happen. It's going to jump over here, okay? And the expected configuration for gold will be xenon, and then it'll be 6s1 5d10. Okay, just remember to fix this part over here. I had put 3d there by accident before. It was 4d. And now these are the correct configuration. So this will be the configuration, the real configuration for copper. This will be the real configuration for silver, and this will be the real configuration for gold. They don't follow the same pattern, and that's why they are known as anomalies. Okay, anomalies simply means they don't follow the normal pattern. They're exceptions. Okay, so I hope this helps in covering these 5 exceptions. There are other exceptions in the periodic table, but these are probably the most common 5 that you're going to encounter. Okay?